Hello everybody, we meet again. So we continue with the value at risk. Today we're going to talk about um, the a methodology to determine the value at risk. So this is a so-called non-parametric methods where there's no assumption, and then uh, not only for returns but also for the volatility. Okay, so we briefly go through. So this method is called historical simulation. This is historical simulation. Historical simulation. So it looks like very fancy terms, a name. Simulation. Basically, this is the easiest method. Okay, so this is one of it is non-parametric. So you have parametric and non-parametric methods. Where in parametric methods, you need to assume that your data set or your return series is following a certain types of distribution, for example, normal student t. Okay, but non-parametric, there's no assumption of that. So secondly, it actually uses a historical data, so historical simulation. So using historical data. So if you have a returns, so this is for return series. Okay, for return series. So basically, there's no assumption. Okay, no assumption for the distribution about the uh, normal or other types of assumption. So the procedures are quite simple. Procedures. So first step, uh, you're going to collect the data. Okay, just collect the historical return. So you have a return series, let's say for 100 days, 200 days. So let's say 100 trading days. Okay, maybe 3 months or 4 months ago, 100 trading days. Okay, so next one is just doing a ranking. Very quick, you can do a ranking. So ranking basically from worst to best. Okay, for example, you can have a series. Let's say you collected the data for 0% is here. This is positive, this is negative. Okay. Then for other percentage, so this is a frequency basically. The bar representing the frequency. So in this way, we just rank the worst. This is the worst, isn't it? Let's say minus. So this is a return. So let's say this is minus 7%. This is plus 8%. Okay, so this is the best returns within the 100 days trading days. Okay, so the third step is quite straightforward. You just need to choose the percentile of the confidence level you want. Okay, so pick the percentile. So if you divide your data into 100 intervals, then you're going to have each interval representing 1%. So you have a 98% percentile and so on. Okay, so this is divide into 100%. If you divide by 4 parts, then you have quarter. Okay, quarter 1. So in the box plot, most probably you divide into 4 parts. Is it Q1, Q2, Q3? Okay, so pick the percentile. So based on your confidence interval, confidence level, sorry. Confidence interval is the estimation. Okay? Confidence level. confidence level. So let's say if you talk about 95% confidence level, then you should go to the fifth percentile, right? Percentile. Right? So from here to here. So the worst 5%, in other words, okay, the worst 5%. Okay, then lastly, you just need to calculate the amount of money or the possible loss. Okay, possible loss. So if let's say your capital is 100k, then let's say the fifth or the percentile, the worst return. Right? So let's say somewhere around here, the worst return. Let's say in this case minus 4%. Okay, minus 4%. Then your VAR can be easily determined by the capital times the 4%. Okay, so this is 0.004. So the possible loss is 4,000. Okay, so this is how you determine the value at risk using the so-called historical simulation. Sounds fancy, but this is very easy to implement, isn't it? And we don't need to have any assumption about our return series. Okay, our return series. So of course, if you look at this, the advantage is what? It's easy to implement. Right? I think this is the advantage. Simple and intuitive. So of course, second is no assumption needed because it is non-parametric. Right? So the not very good thing is because disadvantage or limitation. So the first one is history may or will repeat because you're using the historical data only, right? So not able to capture the, let's say the historical data does not consist of extreme values, okay? Not able to counter extreme values. If historically you don't have these extreme values, then most probably because you refer to historical data, you're not able to capture any real cases, okay, like extreme values. So for implementation wise, this is quite easy. So let's say we use the Excel. First of all, we are able to generate, so we're going to simulate normal random numbers. So normal random simulation, the first thing is you're going to generate a value between 0 to 1. Okay. So from 0 to 1, if you want to generate a normal random numbers, so you use the normal inverse to get the z value. Okay. So this basically will provide the z value for us. Okay, so you have let's say the distribution of this. Let's say this return, we're going to simulate the z value. Okay? Z value. So the z value, as you know, can be from negative infinity to positive infinity. So how do we generate this? So first of all, the quanta here representing the probability from 0 to 1. Okay, let's say for 100 days, we simulate the value. And then we use the normal inverse to get the, where's the diagram I just drawn just now? So the z value will be using, so this will be the z value. Z value. Oh, I see. Why it just disappeared? So this Z value basically is random every time you run it. Okay, every time you run it. So for example, if you try to run it, because this random number is going to change every time you refresh it. Okay, so this is the normal random number 100. Okay, so every time you run it, you get a new uh, curve. Okay, you get a new curve. So like this one is very close to a symmetrical normal distribution. Okay, so in this case, because for standard normal distribution, the value 99.7% will be fall between -3 to +3. Okay, as you can see, the value is always between -3 to +3. So no matter how many times you run it, you get the value close to -3 to +3. Okay, and then the mean will be close to 0 because we know that the Z value, the standard Z value will have a mean 0 variance 1. Okay, so you can see the simulated value will be close to that. Okay, every time you run it, close to 0, close to 1, close to 0, close to 1, close to 0, close to. So you keep on doing this for a few thousand or 100 times, you'll get similar result. Okay, so how are we going to, okay, let's say we have this, so this representing the Z value representing the return, isn't it? So let's say we just copy this, any of the simulated series will do. Okay, so we put it here, so we just paste by value. So now we're going to rank it. So as we have mentioned just now, the first collect the data. So this one you can get the actual value or the simulated value. So actual value you can go to Yahoo Finance to get the data. Okay? So second step is ranking. Okay, ranking. So now we rank it from the smallest to largest, isn't it? A to Z. So sort smallest to largest. Okay. So we just want this row to be changing. Okay. So the smallest value is -2.4%. The largest is so the 100 2.6%. Okay. 2.4 to 2.6%. So the next thing we need to do is pick the percentile. Okay, if you're talking about the fifth 95%, then you just choose the fifth percent, the fifth smallest value, worst value, 2.04548. Okay, so times 100,000, this will be 2045 dollars. Okay, the 95% var. Okay, you're talking about 99%, then this will be uh, the second, this is the fifth one, isn't it? The first one, 2,400, and I mean just times 100,000. Okay, 100,000. So if 10%, then this will be the minus, or minus means the loss. Okay? So 1,600 and let's say 1,609. Okay, dollars for the 90% confidence level. This is 95% confidence level. Okay. Okay, so the var basically, you can just say the var will be, so this is one of the example. Okay? So the var will be 100k times, what is the percentage? 2.045. Okay, 2.04%. You can just do this. 2.045%. Okay, at the end, the var will be 2,045,000. Okay, so this is under a normal random numbers. Okay, normal random numbers. So, but most of the financial data, instead of following normal, which is underestimated issue, because the extreme values will be much more higher than that. Okay, so now we can change this to a t distribution. Okay, with the degree of freedom 5. So if you do so, you will see the plots of the, so this is a simulation. This is a simulation for T simulation. So this simulation is based on student T. Okay, so you can just see the extreme value is more than 3, isn't it? So this one minus, so this is more than around 4 already. So you just assume that this is return now. Okay? So the return can go to 6%, and then the worst one can go to minus maybe 6%. Or normal is always between -3 to 3 now. Okay? So student T can have a heavier extreme values involved. Okay, so this even go up to 7.5. Okay, so the worst depends on, this is every time the simulation will give you a different result. Okay, this is by chance. Okay, this is by chance. Okay, so you can go up to plus 20 as well, because it is just simulation. Okay, now we just get one of the data. Okay, this particular data, we just copy this and then do the same thing, paste it on one of the simulated result values. Then we get this specific value. So for the 5%, you can see this is 5.7. Oh, sorry, we haven't ranked it yet. Just need to rank this first. Okay, so from the smallest to the largest, where's the ranking? We need to rank the data. So where is the ranking? We just go to home and then go to editing. So the smallest to largest again. Okay, smallest to largest. So just rank the particular select. So this one is 2.51%, and then this is, so for example, 2.517. Okay, so the var for the student T will be, let's say, 100k times how many percent? 2.51, 2.517. Okay, percent. So the var is $2,570. Okay, so you compare with this is around 2,000. This is 2005. So the heavier tail actually can overcome the so-called underestimate issue, because you assume that all the returns will be fall between -3 to 3. Okay, but somehow in the financial data, this is much more higher, because you have a lot of, the market is very sensitive to market information. So the speculation actually can cause the loss will be much more higher than if you assume it is normally distributed. Okay, so this is a simple way to do a calculation of value at risk using the so-called historical simulation methods. Okay, in the coming session, we'll talk about how are we going to use the parametric methods, okay, to determine the value at risk. Till then, okay, see you guys in the next session. Bye bye.